Hello everyone, my name is Anthony Shivkumar, and in today's video I wanted to introduce a free tool by Analog Devices called LTSpice. And I've been trying to figure out how I can use, cheap alternatives or cheap products in order for me to simulate certain circuits. And LTSpice is one of those simulation tools. It's a spice tool and I've heard it's really good. And if you go on, on a search engine and search for LTSpice, you'll get this. You can download it from Analog Devices, and I've already downloaded the circuit. And in this video, I want to introduce you to the tool of using LTSpice, and we'll start to simulate a simple RLC circuit. Now, there's nothing simple about an RLC circuit as far as I'm concerned, because a lot of things that happen in signal integrity can be characterized through an RLC circuit. And if you have a circuit that can represent so many different types of configurations and models, there's nothing simple about it. It's fundamentally an important circuit. So I thought that since everyone studies this as soon as from physics 101 to electrical engineering 101, and the applications are never just keeps hitting me all the time. It's like, oh, this is model based on an RLC circuit, and like, yeah, sure. So it's a good idea for me to demonstrate how you can simulate an RLC circuit using LTSpice. So I've already downloaded. As of this recording, the current version is as of now the current version is is the one that was there updated on March 24, 2022. And I'm pretty sure by the time you watch this video, it might be already outdated. So that just shows you that, and right now is somewhere around May. So my point is, like, it's updating like every, if it's just 2 months older version, it's a very active product that is definitely being maintained. So before we even dwell into creating a simulation of the LTSpice model, let me just show you the workarounds of how you can create a simple RLC circuit. So in order to create a new schematic, you can click File, New, and then you have a new schematic, and it'll open up this nice little window. And here you have all the resistors and the components, basically the resistor, the capacitor, the inductor, a diode, and then you have components. Now, the interface does you need to get a little used to, in the sense that after using some other Spice products, I find this a little bit tricky in that sense. And I'll show you what I mean once we start to model circuits. So it's very simple, it's very clean, and there are only 3-4 components, because the configuration of those components really define how you want to model your circuit. So let's create a simple RLC circuit. So the first thing that we need is a voltage source. And as you can see over here, there's no voltage source as such. So in order for you to get a voltage source, you got to click components. So as soon as I click components, it'll open up this window. And here you have a lot of windows. You have, references, power, and these are all generally from the Analog Devices, their repository of components. So we just want a simple voltage source, and we want to basically test the step response of an RLC circuit. So I'm going to basically include a voltage source over here and click OK. And here we have a simple voltage source. And one shortcut that you could apply is, if you want a resistor, because we're creating an RLC circuit, I can just type in R and it will take an R over here. And if I want to rotate it, I can click Control R and it will rotate it. So Control R is for rotate. So we have an R over here, and I can click an L and I'll get an L as an inductor. Control R to rotate it, Control R again. And then we have an RL, and then let me put a C. And then we have a C. And then I want to ground everything, so I basically can put a ground over here, or a return, and another return. And in order for me to draw, I click Escape, and then I just click Wire. And here, let's basically try to get the wire going. So wire 1, wire 2, I'm basically just connecting the wires. And there we go. And here we have a very simple RLC circuit. Now, one thing you might have noticed is that it has populated the values with V, R, L, and C. Now, so by default, if I click on this, say the the resistor, and this is where it gets a little annoying in my opinion. It's like cursor and the clicking, it's a little used. You need to get a little used to because it's not necessarily very intuitive. But anyway, so here we have a resistance, and it says R. So let's basically put this as 50 ohms. So if you leave it, it'll give you it will basically give you 50 ohms. You can also select resistors from a specific part if you want. In this particular case, let's keep it simple. Similarly, let's put an R, and here on R I will for an L inductor, the same thing. You can right click, I think, and then it will give you what you want. So in my case, I'm going to put an inductance of say 100 nano Henry. So I can just do NH, and it will basically be able to understand it's nano Henry. And similarly for the capacitor. For the capacitor, I'm going to put say 1 picofarad for now, and we'll see the circuit. We'll try to compare it with our mathematical model as well. And then here, for the voltage, now as you can see over here, it says DC value, and because we're doing a step response, we want to basically simulate a pulse, right? So what I'm going to do is I'm going to click advanced, and then here it does have a pulse option. So I'm going to click pulse, and as soon as you click pulse, it'll give you a lot more options related to pulse. Let's have the initial voltage to be 0 volts because we want it to start at 0, and the on voltage to be say 10 volts, just to give us I mean, you could also put a 1 volt and it would scale automatically. And the time delay from it to switch from 0 to 10 volts, let's put this at say 1 nanosecond, or maybe 1 nanosecond, or maybe 10 nanoseconds. The rise time, let's put this at 1 nanosecond. The fall time, because it's a pulse, has 1 nanosecond. So this is a very actually, you know what, yeah. And then let's put T on, how long we want this to be on. Let's put this as I can put this as 1 second. The period can be 10 seconds, so it's a 10% duty cycle. And we don't need to put number of cycles. And I'm just going to click OK. And so we have our pulse basically, and all the parameters for the pulse kind of defined over here. All right. So let us simulate the circuit. We have our variable. So all you got to do is now click simulate, and then click. You want to control what we're trying to simulate over here. So this is important because since we're doing trying to figure out the transient response, we want to know what the stop time is. And let's put stop time to be say 100 microseconds. Time to start saving, and the time step. So over here, I'm going to put this as 1 nanosecond, so that we're able to see the transient response. It's going to take a little while, but let's see how it works. And now let's simulate. And when I click simulate, it will try to basically create a window to show the graph. And if you want to now see when we want to see a voltage, so what I can do is let's show the step response over here. So as soon as I click on this, it'll show me the step response. So it's going from 0 microseconds to 10 microseconds. And if you want to zoom in, all I got to do is just basically show me. I just want to see the actual step response. So here you can see that it's going, and here you can see that it's taking the 1 or 10 nanoseconds that I had expected it to show, that I had basically asked it to take. It'll take around 10 nanoseconds for it to go for the rise time, and the rise time is 1 nanosecond. Now let's look at how the voltage transient looks, how long That's when all I got to do is just take this cursor and just click on where I want it, and then it will show you. As you can see, there's a lot of ringing, and it's primarily because the rise time is so much more, is really short. And that's how you can simulate a simple RLC circuit. If I want to increase, say, my and then decrease the ringing, I could decrease the RC time constant. One way to do that is to increase the rise time, and also I can increase the L and the C as well. So what I can do over here is do a cancel over here, and then let me make this instead of 1 picofarad, let's make this a 1 nanofarad, and let's see what we get. All right, and we don't need to simulate for too long, so all I'm going to do is click simulate. I'm going to edit the simulation command, and instead of simulating for 100 microseconds, I'm just going to simulate for maybe 1 microsecond, and the maximum time step is 1 nanosecond, and let's click OK. Okay, and then we click simulate, and then we run. And now you can see that there's much less ringing, but because the RC time constant or the RLC time constant is a lot longer, it takes a longer time for us to reach the step response. And if you want to delete the variable, all you got to do is basically click on this and right click, and then it'll open up a small little window over here, and then you can click delete the trace. And similarly over here, I can click delete the trace. What if I want to measure the current? Say I want to measure the current through the inductor. So one thing you'll notice that if you hover over in the inductor, it will show you this current symbol, and that symbol basically says that we can measure current. And from here, you can really see that this is measuring current because the unit is in milliamp. And it basically says that because there's a response, there's a high peak current that's flowing through, and then basically it stops. So what does an inductor do basically? So if we know what an inductor does, so the voltage across an inductor is equals to L di by dt. That means if there's a change in the amount of current, then the voltage is then there's a lot of voltage. So that means, it basically means as soon as there's a step response, there is a sudden change in current. So let's measure even the voltage over here, the output. And this basically says that we're kind of like open circuit, and as we reach a specific and once the inductor is once there is no more transient, the di by dt is died off, then we have L di by dt. Di by dt is almost 0, so that means the voltage across the inductor is also a 0. That means it becomes a short circuit. So you can think about it that way. So, and based on that, you can see the amount of current that is flowing through. So we can even see the current flowing through the resistor, and it'll show you the current flowing through the resistor is this I over here, and as you can see, it goes from 1 volt to automatically to 5 volts. No, sorry, this is the current. So what I can do is I'm going to basically hide out all the voltage so that we can see the amperes. Delete the voltage over here, and delete the voltage over here. All right, and then you can see the current. That's so the blue one is the one that's going through the resistor. That's one over here, and then we can see the one that's going through the inductor. And the current through a circuit based on KVL and KCL will always be a constant. So, so the resistor in the beginning, I don't know why it's going in negative. This is something that I need to understand. But over time, it basically has it eventually dies down because there's nothing driving it. Because the current flowing through a capacitor is I is equal to C dVc by dt. The voltage is a constant, is a step, so it's technically an open circuit, so nothing is really flowing through. So the voltage will be exactly the voltage in the input. Now let's put a load and let's see what happens. So in this case, let's add a load. So I'm just going to put an R over here. So let's put some load and ground. And now there should be some current flowing through. So now let's put the wire. And now let's simulate. We're not put the value for the resistor. So I'm just going to right click, or I'm just going to put this as, say, 100 ohms, something to flow through. So if we have 10 ohms, so the current flowing through it is I is equals to V by R. So 10 divided by 100, so we have about 0.1 amp or something of that sort. You know what? I'm going to basically increase this voltage. So this voltage right now is 10 over here. I is equals to V by R, so 10 divided by, I'm going to make this 1. And then let's see what happens over here. 1 amp, and here also I'm going to put this as 10. So there should basically be 1 amp flowing through this part of the circuit. 10 divided by 10 is 1. And then now let's simulate. Yeah, there we go. So now you can see it's almost close to 1 amp. And that's something that makes more sense because the current flowing through this is equals to 10 volts. I is equals to V by R. V is 10 volts. R is 10 ohms. So you should have something close to 1 amp. And then here there is another current flowing through here. So let's put the current flowing through here. And it'll all be the same because current through the circuit will be the same. All right. And then what's the current through the inductor? So the current through the inductor, which is the IL, it first has a, let's see, where is this? IR. Let's clean up a little bit. As you can see, it's pretty easy to use the tool, and it's free, it's straightforward, it's supposed to be pretty powerful from what I've heard, and from what I'm seeing, I really like it actually. So I'm going to put the current through the resistor, so it's pretty straightforward, and it shows me that it's almost 900 milliamps, almost close to 1 amp. And then let's see, the one to the inductor is also going to be the same, and the current through the resistor. So the current through the original resistor, yeah, this is where I'm not completely sure what's happening over here, and why is it going negative. And that might be got to do with the, yeah, is the direction in which I am actually showing. And so does that mean that I can, yeah, it's the direction in which it's showing in the direction. Okay, so that's the reason why there's a confusion. I'm not too sure how I can change the direction. I'm still trying to figure that out. And then, so this is how you can measure current. So the direction is important because it's showing the direction feeding through to this voltage source, and that's not what we want. That's the reason why it's saying negative, because hey, it's not going in this direction, it's going in the opposite direction. Whereas everywhere else is pointing in the right direction. So yeah, I need to figure that out. And I think it's got to do with the fact that maybe if I basically cut this and then I do a control R, it's maybe the way I place a resistor. And now if I do this, yeah, maybe I should simulate this again, run the simulation. And now it's looking a lot better. Now they're all the same. Yeah. So it's basically the orientation of the resistor that makes a difference. So the current flowing through all of them is the same, which is exactly what we want to see. And then let me show you the so because the steady state is reaching pretty quickly, all I'm going to do is this. I'm going to simulate this in the nanosecond. We don't need to go all the way to the millisecond. So I'm just going to basically put stop time to be say 100 nanoseconds. And now let's simulate. Oh yeah, now it's looking so much better. And then this is how much time it takes for the current to flow through the circuit. And let's see the voltage response. So you just have to go click on top, right click, and then click delete. And then I can put the step response over here. And the step response will show you exactly between 10 nanoseconds, it will reach, and from 10 nanoseconds, it's 0. And then from 10 to 11 nanoseconds, it takes is the rise time. And the output voltage over here is so V is equals to so there is a significant drop, and the voltage is 1 volt over there. So the V is equals to I into R. I is going to be around 1 amp, and R is also going to be 1 ohm. So I is going to be 1 into 1, which is equals to 1 volt. And yeah, that is exactly 1 volt. So in order for us to reach 10 volts, let's try to make this as 10. So let's put this as 10, and then this should be, I think, 10 volts from my understanding, from my calculations. Okay, so let's simulate again. We'll observe the blue, and the blue is still it's now reaching 5 volts. So because it's a voltage divider circuit, 10 into 10, and then you'll have 5 volts in the middle at steady state. So I would have to put this, I believe, around 20. I'm getting there. I'm not modeled the circuit, so the actual mathematical model we will have to do through MATLAB. So what I will do is I'll open MATLAB with these numbers, and then we can see what the voltage is. So let me go to MATLAB, and let's say, so the input voltage is 10. I'm just going to write this down. So the input voltage is 10. The R1 is going to be 10. RL is going to be 20. L is going to be 100 nanohenry. And C is going to be 1 nanofarad. And the voltage is over there. Okay. So based on my circuit over here, let me open MATLAB. This was based on the previous thing. So we have two different I'm going to basically do this run section over here. So it's going to clear and clean everything. And then let's model to see what the voltage is in here. So the R over here is going to be 10. The R1 is also going to be 20. C is going to be 1 nanofarad. So that's 1 into 10 raised to minus 9. And the L is going to be 100 nanohenry. So it's going to be 100. And we're going to put this as minus 9. And now let's run section. And here we get a step response. And here we have a step response of, because the step response is always going to go from 0 to 1. And in this particular case, it's around 0.7, 0.6, 0.65 is around the circuit. So let's basically scale that down and see where are we. So this is 10 volts, so we just have to make sure it's around 0.65 based on our mathematical model. And as you can see, it's very similar. So the current is basically, the voltage is basically the V over here, because these two are, so this is the step input, the green, V is the voltage, and I is the current. So V is this, and this is very similar to what we modeled mathematically. So yeah, it is right. Based on modeling the step response. If you want to know how I did the MATLAB version of it, there you can watch the video where I basically demonstrate how I hand calculate the RLC circuit. So yeah, that's about it. And as you can see, it's pretty good. I mean, as far as I'm concerned, it's for what you're getting, and it's free. It's very powerful simulation tool to simulate circuits like this. And you can just go nuts playing around and making sure your intuition is whether what you're predicting and whether your hand calculations. And that's the reason why I'm using MATLAB, to make sure my hand calculations are matching what the simulation results are doing. There are a few things that I believe that are better in some of the paid versions, and I will do a video on comparing different softwares like from Keysight ADS, LTSpice, even the one from Hyperlinks by Siemens, and maybe even PSIM from PowerSim, and see what all these different tools provide, and what I feel is good for what type of circuits, because some might be good for power electronics, some might be good for digital electronics, and some might be good for just simulating some signal integrity issues, and just basic electronic circuits and analog circuitry. So based on that, I hope you enjoyed this video and you like this video. And if you haven't tried working with LTSpice, I highly recommend trying it, just to get your feet wet, to see whether it's a tool that might help you out. As far as I'm concerned, it's very powerful. It's very easy to use. There are a few user interface issues that I'm not necessarily comfortable with, but that doesn't take away from the fact that if I want to simulate an RLC circuit, and if I want to map it with my intuition, this is a fantastic tool to do so. Having said that, I hope you enjoyed this video. Do like to subscribe, and until next time, stay safe.